words in, but a lot of people said positive 333, yes. Then compound here, I asked you to do two types of isomerism. One was skeletal. This started off as an aldehyde with a 5 carbon chain, 1, 2, 3, 4, 5, pentanal. I put that there for reference. And again, the sort of mistake people made was they redrew this with the CHO over on this end. It's the same molecule, whether you go forward or backwards. So, skeletal, you could put the methyl group here, or you could put the methyl group here. Doesn't matter. The way I did it was 3-methyl. If you put the methyl group over here, it's 2-methyl. And I did C1. That said 1-methyl. And I said, anytime you're saying 1-methyl, what does that mean? You didn't find the longest carbon chain. That's what it means. You should have started counting one sooner, because this is still a 5 carbon chain. Some of this I say so much, sometimes people don't remember what I said. Okay, and then the functional group, and I gave them to you in pairs. So the pairs I gave you, you can have either an alcohol or an ether. Those will make functional isomers without any major changes. If you made major changes, because somebody put a double bond in there and did something else, an OH, I guess, and that would work. The problem is they had trouble naming the double bond in the OH. That's why we break the molecules apart in the middle nowadays. So I just changed it from aldehyde to a ketone. It could be 2-pentanone or 3-pentanone. Either of those would be good. Anything else? Questions? Yes?
For A, is it wrong if we have the 1?
Yeah, because 1-methyl means you didn't find the longest carbon chain.
No, I mean for the null. For the null portion, saying where the bondo is.
Oh, no, you can put it on this side or that side.
I was saying, but if you did -1, you null.
No, it's wrong to say 1 because this is where the carbon chain has to be numbered from. This has to be the number 1 carbon. You can't have an Al in the middle of the molecule because that becomes a ketone. So you never say 1Al. That was your question?
Yeah.
Yeah. Because it has to be 1. And one of the rules still carry over from the old days. If it's really not necessary, don't say it. That's why, for instance, it's redundant and wrong to say 2-propanone, but I said when I did the lecture, you see that on the reagent bottles. But more commonly, what do you see? That was an excellent quiz question, by the way. Acetone. See, I say the same things every year. That's why you don't want to come back next semester. Because you have to hear the same words again.
Trying not to.
What? Okay.
Try that. Look at us fighting for it.
Next page. Most people were okay, except some people jumped to the answer without showing me sufficient detail in the setups. So I said, how did you get this? And some people even had the wrong setup and still came up with the right answer, which was really amazing. Okay, so most people recognize, one of the big mistakes, about 2 or 3 people made this mistake. Where is it? Right here. Ka1, Ka2, H+ squared, sulfur over H2S. What do you see down here? Whoops, did I go far enough? I didn't go far enough. There it is. K1, K2, H+. If you didn't remember, it was right there. Okay? And some people looked at, I don't know if they looked at it or they did it from memory, but about 3 people did H30 plus to the first power instead of squaring it. Okay? Are we going out of focus? What? There. So basically, if you look at the cell, if you want KSP, you need to know nickel ion concentration, sulfide. I gave you the H2S concentration, I gave you the hydrogen ion concentration. If you know 2 of the 3 on this side, you can solve for the third one using this relationship Ka1, Ka2. Okay? So that's what you had to do, and people missed the square. And a couple of people couldn't solve that equation for S2 minus. They just put Ka1, Ka2 with this and said it's equal to S2 minus. That's called what? I talked about this in 1A, I haven't talked about it here. It's called bad algebra. Okay, so you have to be able to do algebra. So that was that part. What up? So you got the sulfide ion, and here's the electrochemistry part. It's a concentration cell. I said whichever side was the anode, cathode, whatever I said. And yeah, that's the way the reaction went. What did I say on that? The right electrode is the cathode. So the 6.50 is the one that's reduced. The other one is the one that's oxidized, so that's the way it has to go. And this is the way you want to set up the ratio. Question? You don't want to ask me? No. Okay. I probably know the answer. So anyhow, you go through and get the concentration of the X, which is the concentration of the nickel. What did I miss here? Oh, I didn't show you the one step here. It's, in other words, this is equal to this, so you have to cross multiply. And then you just have to plug in the equilibrium expression. I can't think of anything that really went wrong there. And this is the same sort of question in the backwards direction. I gave you KSP. And the most common mistake was people put the thallium, this concentration, into here instead of the phosphate. That's when it pays to write this part out, because they just wrote the equilibrium expression like this, and they knew they had to divide by something. And so they picked one number they saw over there, which was the wrong one. So this gives you the TL plus. This is much smaller than this one, so it's this over this. E0 is still 0 because it's a concentration cell. Anytime you see the same electrode on either end, and then you see the same ion somewhere in the middle, you can say that must be one of those cells where at standard states both half cells have the same cell potential. But most people got this right, except for a couple of people that mixed up which number goes into the KSP there. Okay. And here people confuse themselves a lot because they kept trying to reverse equations when they didn't need to. I said on this sort of problem, you always want to start off, even if it doesn't ask you to do it, by calculating the standard state cell potential. And that's easy. Always take the larger number minus the smaller number. Now what a few people did, they reversed this equation and changed the sign. And they looked at these two numbers and took the larger minus the smaller, and they changed the sign again, and they came up with something like 3 volts. So about 4 or 5 people did that. In other words, I said there are 2 ways of doing this. If you reverse an equation, you change the sign, then you add them. Just the way they're written here. Or you take the numbers from the table of reduction potentials and you always take the larger minus the smaller. That always gives you a positive cell potential. And then the fact that you change the sign with this minus sign here, making it change the sign, that's the one you want to write as an oxidation. Okay. Then you just want to combine them. About 2 or 3 people didn't put in coefficients, they just put BE2 plus NP and P3 plus DE. And of course that's not a balanced equation. Then you went to cell potential. There's a 6 electron change. That's the number I needed to see. So a couple of people just put N, and I don't know if they didn't write this, but they came up with the right answer, and that always makes me suspicious, and I did take 1 or 2 points off there for that reason. Okay. So you always want to show me this setup. And the biggest mistake, people had this equation, but they forgot to square this number, cube the other one. That was another more common mistake. A few people got the equation backwards, and then they had this ratio upside down. It should have still worked out to give you what it would have done if you got this backwards. If you did it correctly, it would have given you minus 1.106, and that would have told you started with the wrong equation. But this one, you went through the calculation, came up with plus 0.106. That means the equation is the same in the cell as at the standard states. And you still calculate a positive cell potential. But a couple of people said, oh, well, he always makes it change directions. So they changed the directions just to be on the safe side. And unfortunately, that made it wrong. And there were about 3 people. What does it say? And I said this specifically in lecture. I said, if I tell you to write the equation, even if it's the same equation, you write the equation. That's what I said in lecture. So they just didn't bother writing it. They didn't even say the same. They just didn't bother writing it. Even though the data said they shouldn't have changed it. And then there were a couple of people that said the data said they shouldn't have changed it, but they changed it anyhow. Questions? Okay. So these you just have to go through carefully. When I grade these, I have to go from top to bottom. I can't jump around because I have to follow your train of thought so I know where to put the X's. Next one, it says calculate delta G. This is not delta G 0. So that means you have to use the actual cell potential. Notice if you had to reverse it, you would use the reversed number with the opposite sign. But this one you didn't have to. But, you know, in the problem that we did in lecture, the equation reversed, so you had to change the sign to get the cell potential. And the reason for that is, this is the spontaneous reaction in the cell. That means delta G has to come out negative. If you're having a spontaneous reaction, you have to calculate a negative delta G. Okay? So, you're putting the plus 106 and minus. A few people messed up the signs. One place they had it, the next place they didn't. What else? That's about it. Okay. Not much you can do there. This one says calculate the equilibrium constant for the equation in part B. This is the same as the standard state equation. That means at standard states, that's going to have what? A negative delta G, and you're going to have a large number for the K. Most people got a negative sign in there, and they put it in right here. And look over here. At equilibrium, because E cell is 0 at equilibrium. So when you solve that, it says what? minus sign, or you bring this over with a plus sign, whichever way you wanna say it. But people came up with a minus sign here, that's why when I wrote the answer there, I put a big plus there, because that was to remind me, that's where a lot of people had a minus sign in their equation right there. Okay. And notice, this was the most popular answer, 0.038, which is the reciprocal of this number. And then there was somebody that had all the equations wrong, and they still had this number, but they had the right numbers in there. Well, they had to have the right standard state cell potential, and you're just playing with numbers there. This is the over 1/4 of the standard state cell potential, because this is always standard state when you're calculating the equilibrium constant. And then you had two chances of being right. It was either MP or BE. I wrote N with a cap. I wrote N capital P, so I had to rewrite it. It's capital N lowercase p. It's either beryllium or NP, because those are the two ends of the cell. You had a 50% chance of guessing right. But you would look at this and say, here's the oxidation, anode oxidation. This must be the anode electrode. Okay, any other questions? No other questions? You checked my addition, because I was getting late and I was rushing and adding, so make sure I didn't cheat you out of any points. No other questions? Let's meet over there in about 10 minutes.